Uh, last last day I start from here. I mean, I discussed this one. If they have given a percentile and you need to find that particular x value, simply you have to get simple p is that percentile as a probability, not a percentile as a probability, and doing this integration, you can find doing these integrals, do you can find that value. Okay, that particular x value on the x-axis. Okay, same here. If they have, so I discussed this. I think yes, I explained this one, right? Okay. So they have mentioned 90 fifth percentile. So P is 0.95. Then integral from 0 to a, you need to find this simple a. Okay. Do this calculation, and finally, as I mentioned, you will get a, most of the time you will get a quadratic equation. So definitely there are two roots. So you have to pick which root is the appropriate for your question. Okay, that based on your range of the x. Okay, so that value should include in your x range. Okay, the other one you can throw it out. That's why 1.94 came here, and this guy goes out. Okay. Same thing if you consider median. Median mean, you know, median is the midpoint of your data set or your distribution. So midpoint, which means 0.5, right? So in another word, 50%, 50%. So same here, you have to replace, if they ask 50th percentile, which means simply it's median, 0.5. P is 0.5. Very simple, P 0.5, and you can do the same calculation to find the F mu or F eta. Here mu tilde because of the median. Okay, notation doesn't matter. Same thing you have to do. Okay, if here this some kind of a note, if your distribution is symmetric. Okay, symmetric mean something like this, symmetric. Okay, then median will be equal to the point of that symmetric, that axis. Okay, so this is like symmetric about this axis, right? So your median going to be this point, something like that. Okay. uh, Anyway, how to find the expected value? Expected value same as that particular variable x. Sorry, for the CDF, PMF case, we found expected values like summation x times px, right? So same here, but here we have continuous variable. So we can find mu, or we call mu x, or we can call expected value of that variable, equals to summation, which means here integral from its beginning to from its lower bound to upper bound, x times fx dx. Okay, this is x, the variable function of that variable, whatever, like if it is a uniform distribution, 1 over b minus a, something like that. Okay, so using this you can find the expected value. Okay, same here, expected value mean mean of that population. It's exactly same as the mean of that population. That's why we denote by mu. Okay, so this is your function. I mean, this is your PDF, probability density function. Okay, so this is the range of the x. So within this range, function is defined like this. Okay, it is defined like this. If x values are not in this range, which mean less than 0 and here greater than 2, right? Function value is 0. Again, it is also defined for other values as well. It is 0, right? So how do you find expected value of x? Simply, what is the definition? from negative infinity to positive infinity, your variable here it is x, function of that x dx, right? So what is the range? You can replace this negative infinity and positive infinity using your lower bound and upper bound in your problem. Okay, so here 0 to 2. So simply replace those two, 0 to 2, x times fx. So your function is this times dx. So do the integral and then plug the upper bound and lower bound, you can get the answer. Okay, clear? So this is the expected value, which means a mean. So it doesn't matter what's the value. It can be a negative value, 0, positive value, whatever. Okay, clear? Okay. What is this? Okay. What happens if we have a function instead of just a variable? Same as previous chapter, we simply replace your x using that function. Okay, hx means a function of x. Okay, like x plus a is a constant, something like that. Okay, so simply plug that function instead of x and do your calculation. Okay, so next slide I'll show you the we don't have that one. Okay, for an example, your hx, let's say x minus 200, something like this. Okay, so using previous case you can find let's say it was 0 to 2, right? Something like that. So x minus 200, this is your hx. Okay, this is an example. Okay, don't try to solve this. I don't know whether you can find this, but this is how you do it. This is your x now. Okay, hx times your function. Let's use previous case, this one, 1 over 8 plus 3 over 8 times x. This is your fx times dx. Okay, you can use dx here because hx is again function of that variable. Okay, so variable doesn't change, no problem. Okay, clear? But you will be having a little bit more work to do here for this calculation. Okay, so okay, variance. We have expected value and variance for particular distribution. Okay, so variance normally we call population variance sigma squared, right? Or you can denote it by like sigma squared x sub this one, same here. Okay, sigma squared or sigma x squared or sorry, variance of x, capital V mean variance. You have to again do the integration here from negative infinity to positive infinity. This is the x minus mu squared. That is the function we use to calculate variance here. Okay, so they are very similar. When you find the expected value and variance, they are very similar. Difference is here. Okay, but there are two easiest way to find these variance without doing this integral stuff. If you remember, I think it's in next slide. So simply they have taken this expected value of x minus mu squared by simplifying this. Okay, so you can take x minus mu squared and expected value of that to find this. Okay, let's say you have capital X here is the continuous random variable. Okay, so mu you can find this is what this means, expected value of x, right? So you can find this guy from the previous slide. Oh, sorry, this one. Sorry, this one, right? And do your calculation again. Here you have expected value. Okay, simply this one. Expected value of something. Function of, see, expected value of function of x, right? So that's the similarity. I want to show you the similarity. See here, expected value of function of x. Same here, expected value of function of x. So now your function of x is this one. So simply plug that times fx dx. Okay. Standard deviation, which means square root of the variance. Okay. So if you replace this, here you have expected value of capital X minus mu squared. So you can simply replace what I have mentioned here. Minus mu mean expected value of x. So you have squared like this, right? So if you simply simplify a little bit, you don't need to do that. If you simplify what I wrote here, then you can get, I'll show you this one, this. Okay, you can get this by simplifying what I wrote in the last slide. Okay, so variance formula for the variance, you can use this one instead of the previous one, or you can use the previous one, whatever you can use, that's fine. Okay, to find this integral, it is its range negative infinity to positive infinity, x not x, x squared, right? Because you have x squared here times fx dx. Okay, this one, whatever, again negative infinity to positive infinity, x times fx dx, but what after that, squared. Okay, clear? Same, it's very similar to how we deal with the discrete variables. Okay, same idea. Only difference is last time we had summation notation, summation, just sum. Here, yes, still sum, but we are dealing with integrals. Okay. Okay. Same example. Okay, same example. We need to find the what? Oh, variance. So simply, as I mentioned, you can calculate ex squared and ex, right? So this x squared, as I mentioned here, see this one. Okay, its range x squared times function of x. This is your function of x times dx. You have this, and simply you can calculate fx 0 to 2 x times fx dx. Okay, and you can get this value. Then plug those values and find the variance. Okay. Okay, that's the end of that chapter 4. It is 4.2. Yes. Any questions from this chapter? Let me share the other one. Any questions from the chapter section 4.2? Okay. Now I'm going to start next section, which means 4.3. It is a little bit. Actually, we don't need that one. It's a little bit important. Okay. It is, I mean, this normal distribution plays a huge role in statistics. Okay. Based on, I'll tell you the important of why this normal distribution is important. Most of the time in statistics, while we are doing our research and those stuff, if we have a data set, or simply we call observations, those observations can be like normally distributed or not. Okay, those are normal distributed or not. So if they are normal distributed, we can easily treat them. Okay, we can easily handle them. But if they are not normal distributed, it is little bit hard to treat them. Okay, so sometimes we do we try to transform uh, your data line, which means if they are not normal distributed, we try to transform them to normal distributed data set. Okay, otherwise we just keep it as it is and do our work. So based on our normal distributed or not, we call, if it is normal distributed, we call it parametric. Okay, otherwise, which means not normal distributed, we call it non-parametric. So those are two giant research areas in statistics. Okay, parametric, they treat like totally different if you compare with the non-parametric. So those are two different stuff. Okay, so normally distribution is a very important case in statistics. Okay, okay. Normal distribution. Normal distribution, in general, it has a bell shape. Okay, bell shape. That shape can be like skewed or symmetric. That's fine. Okay. If it is symmetric, mean, median on the where, if it is symmetric, let's say suppose this is my symmetric normal distribution. So mean and median, it is somewhere this point, same point. Okay. Mean and median of the curves are equal. Yeah, a curve are this one somewhere here. Mean and median, if that normal distribution is a symmetric distribution. Otherwise, mean and median can be this side here or here. They are different. Okay. There are two parameters you need to know. Already you know these parameters: mean and variance. Okay. This is standard deviation, which means variance squared, right? So if we need to discuss normal distribution, we need those two parameters. Those two parameters tell us what how this normal distribution is behave. What are the characteristics of that normal distribution? Okay, using those two parameters only. Those two parameters are mean and variance or standard deviation. Mean, normally we denote mu. Standard deviation or standard deviation we normally denote by sigma, or simply we use variance, sigma square. Okay, clear? So this yeah, this place, let me, yeah, I'll explain that here. Normally in normal distribution, that x range is goes like negative infinity to positive infinity, entire real axis. Okay, so you can trim it like 0 to positive infinity, something like that. That doesn't matter, but in general, normal distribution goes from negative infinity to positive infinity. That's why you can see here, when we draw our curve, these ends, very beginning and the end, they do not touch the x-axis, right? Because it is not 0. It goes to infinity. In infinity, it's 0, yeah, or negative infinity. Clear? That's why they do not touch. So keep that in your mind. When you draw it, that's fine for this course, but apart from this course, please keep that in your mind. We never touch those two together because they are not 0. Okay, because of this. Okay, so completely we can describe, or we can explain our normal distribution by using only these two variables: mean mu and standard deviation sigma, or variance sigma square, same thing. Okay, once you need to denote our normal distribution, simply you can denote, okay, what is your variable? Let's say capital X. X has a normal distribution, capital N. What are the parameters? Mean mu and variance sigma square. This is how we denote the normal distribution. So you know what is the mean, you know what is the variance. Okay, so this variable mean, mu we called location parameter. Okay, we call location parameter, this guy we call location parameter. Location parameter. Oh, okay, location parameter. Okay, and mu, sorry, sigma squared we call scale parameter. Scale parameter. Okay, what is this location does? I mean mu change its position, like, so this is this according to this one, this is your mu, right? This axis or this value, this point. So once we shift this mu to left side or right side, shape of the distribution is changed, right? If you change your mu to right hand side, it's going to be like negative skewed, negative is skewed, right? Clear? Something like that. So distribution, the skewness can be changed using this mu. That's why we call location parameter. I don't know whether you need those two words, but keep that in your mind. Then variance, sigma squared, we call scale parameter because that guy changed the peakness of the shape. So when sigma squared goes like small values, peak goes down. When sigma squared goes higher values, peaks goes up. Peaks, those peak goes up. Clear? So location, scale, they change, but we can change them by using mu and sigma square. Okay. Once you need to denote your normal distribution, you can simply denote it like this. Okay, X as a normal distribution, mean mu, and variance sigma square. Okay. Displays, where is this one? Normally we denote variance, not the standard deviation. That's the general case. Okay, variance. Okay, see, I think they have, yes. See, they have different mean, which mean mu, different mu values. But you can see peak, it is very similar, right? It doesn't change. But mu value, they are different, like they shift. Okay. But if you consider third one, these two, you can see mean value is same, mean values are same here and here, but what happened to their peak? They are different, right? So that's why we call the same mean here, but different standard deviation or variance. Okay, different variance change the peakness of the distribution. Okay, this is how it works. Sometime if we change the mean, distribution can be skewed, or it is still same but its mean change. Okay. Okay. PDF of the normal distribution. PDF of the normal distribution is something like this: 1 over square root of 2 pi times sigma times e to the power x, negative x minus mu squared over 2 sigma squared. Okay, you can simply rewrite this like 1 over 2 pi square root sigma squared. Okay, times e to the power, you can simply write it like exp, right? And take down the powers, negative x minus mu squared over 2 times sigma squared, something like this. Okay, same thing but different ways. Okay, so this is the variable, this is our PMF, PDF. Okay, PDF, simple f, x is the variable, mu is the mean, sigma squared is the variance. Okay, so you know what is mu, you know what is variance, then you can simply calculate the probability values. Okay, but the problem is, once you need to calculate the CDF, cumulative density function, it's really hard to do that, because if you check this, if you get the integrals from this goes from negative infinity to positive infinity, negative infinity to positive infinity, or not, so something like this. Do I have a space? No. If you need to calculate the CDF, what you have to do, you can see, right? Yeah, it starts from, sorry, negative infinity to particular x, right? And your function f x mu sigma squared, right, times dx. Clear? Okay, so you can see that it is really hard to do this calculation because of this guy. Okay, but don't worry, we have a solution for that. We have this. This is our solution. Standard normal distribution. Previous case, normal distribution. Okay, standard. Now it is standard normal distribution. Standard normal distribution is a little bit different, which means x, our variable, has a standard normal distribution. Same way we denote the normal distribution or standard deviation, standard distribution. But now its mean is 0 and variance is 1. This is really important. This is your mean, mu. This is your variance, sigma square. This is the difference between normal distribution and standard normal distribution. Standard normal distribution means always it is mean 0 and variance is 1. So now you can see that once you plug 0 and 1 into this distribution, you will see mu goes away. Then you can what? It's like 1 over 2 pi, right? Because sigma is 1, sigma squared is 1. So exp negative x mu is 0, x squared over 2, right? See, it become very small or very simplified version. Okay. Standard deviation from the mean, yes. Positive values. So if you now you can calculate values, or you can calculate the CDF. Once you calculate the mean, or like we call expected value, you will see that values in this standard normal distribution can be negative or positive. Okay, these values, I mean these x values, we called C values. Okay, C C values. Why we call this C values? Because this is the standard normal distribution. Okay, this is not the normal distribution. We just change the notation here, because otherwise you will confuse with this normal distribution and standard normal distribution. Okay, so everything we deal with C instead of X. I mean C. We call that. That's why we call these values C values. C values mean, okay, standard normal distribution. Once you check these two, you can understand. You should be able to understand. Standard normal distribution is a symmetric distribution because it is mean is 0, right? So it is symmetric about 0. Okay, variance is just 1. Okay, so these are the C values. Whatever here, these are we call C score or C value. C we normally call C score, but sometimes we call C values. So these are the C scores. C scores. Okay, or C values. Here what they have mentioned, C values. Okay, clear? So from here to here, that values are negative, and here to here positive. That's why they have mentioned, see, positive C values are above the mean. Above the mean, see, this is the mean. So positive values are above the mean. Negative values are below the mean. Clear? That's what they have mentioned. Okay. So this is symmetric. This is not the normal distribution. This is the standard normal distribution. Okay. We can deal very easily with this standard normal distribution. Okay. Okay. Standard normal distribution, okay, like this. See, normally we use capital C or simple C instead of X, but it's again a variable, a random variable. Okay, so you can derive your standard normal distribution like this. So we can calculate the CDF. We normally denote by psi Z. Okay, psi C, capital psi C. Okay, but still you can use capital F, but the thing is this is standard normal distribution, so try to stick with this notation instead of capital F. Do you remember capital F? Capital F of C. So try to avoid this in this standard normal situation because it is a little bit different. That's why we use capital psi C. C is the variable. Okay, clear? Okay. There is no formula for calculating these. Okay, obtain them, otherwise software. Those values, I mean C-score values and probability values, you can calculate, but the problem is it is really hard to deal with these. You know how to deal with these, right? Once you need to get the integral, it doesn't change, so that's going to be a problem. But once you need to calculate, you can, I think you can use your calculator. There is a functions calculators, but in general we use computer softwares to calculate those values, or they have done the hardest part, and we have a table. You can see our appendix tables in the appendix PDF I sent you. I mean, I uploaded it to the Blackboard. I think after the CDF of Poisson distribution, you will see there are two tables. Okay, there are two tables. I'll show you a few minutes later. That table, you see that table, you can find CDF values. Okay, so what is the CDF idea behind the CDF? Probability, summation of the probability from its beginning to that particular point. Okay, so same graph here. If you need to calculate the CDF from here to somewhere, let's say here, summation of the area under this curve from it is starting point to this point, right? That's the idea of the CDF. So once you need to calculate the CDF, you can use these software tables, but normal in the class we use this table. Okay, standard normal table. Standard normal table. There are two tables. You can use that. Okay, this one. See, you don't need to refer the book. You have that appendix tables. You can use that. Okay, let's see. In that table, okay, let me show that table for you. Okay, appendix. I need to stop sharing. Where is that? Okay, share. In this table, you remember this table, right? Binomial CDF and Poisson CDF. For those cases, we use this one. So scroll down a little bit. I think, okay, here. This one is the CDF of the Poisson. After that, you can find what we need. Standard normal curve area. So area under this curve equals to the probability. Okay. This is how we find this, how we use the CDF. Once you have to find a probability value, okay, you need the C-score value. If you need to find the probability value, you need the C-score value, which means value of this one, that particular X value, okay, in normal words, X value on the X-axis. Once you have this C value, you can simply come to this table and locates to this particular range. So let's say for an example, C value is negative 3.41. Okay, let's say our C value is negative 3.41. I need to find the probability based on this value. Okay, the area under the curve is starting from negative infinity to this point. Okay, so what we have to do is first try to find the value from this first row, first column. Okay, locate that value. See, we have negative 3.4, then negative 3.3, but our value is 3.41. So this is your row. Okay, now what? You have what you left here. You have 3.4, right? You have 3.4, but this guy is not here, right? You have to find that using the first row. First row mention the rest of the values, this row. So what you left, 3.4 plus 0.01 is 3.41, right? For a moment, forget about the negative and positive stuff. Okay, just focus on the value. Okay, so you need this much, right? So you can find it from here, right? So 3.4 plus 0.01 is what you need. So your probability value is this. Clear? So that's how we find the C value. That's how we find the probabilities using this standard normal table. Okay, clear? I think they have mentioned these things, the same thing in this slide as well. Let me stop sharing. Go back to my PowerPoint. Once you deal with these tables, you will understand how to use them. Okay, and also I think I have already uploaded 2 documents how to use the C table. So you will see that in your Blackboard under the course materials. Okay, okay, using that table, same thing they have mentioned. If you need to find, okay, this is my C value. Probability based on this C value, you can easily find which C value means value here. Okay, so 0.12. So you can go first 0.1, then you left 0.02, find that column. This is your probability value. Actually, this is the area under the curve that equals to our probability. Okay, so your answer is 0.5478. Okay, whatever starts from the beginning to this point. Okay, area under the curve. Clear? Okay, another example, negative value. It doesn't matter whether value is a negative or positive. If your C score is a negative, there are 2, I forgot to show you the other table, same very similar tables for negative C values as well as positive C values. Okay, so there are 2 tables. If your value, your C value is negative, go to the negative C value table. If value is positive, go to the positive C value table. Okay, clear? Okay, see, those values can be like this, negative. I think the first table, negative values, and the second table has the positive values. Okay, so values start from, in the table values start from 3.4, either it is negative or positive, start from 3.4. Okay, if you check those tables, the probability values, you will see that first table start from 0 to 0 and end from area 0.5, and the other table start from 0.5 to 1. Okay, once you check those values, you will see that, because middle point of the distribution, which means it covers half of the area, that's why 0.5. Okay, I think we can do this example and finish today's session, I hope. Yes, C value, you need to find the probability Z less than this value. This is how we deal with this, because we need to find the proportions or the area under the curve less than this value. Clear? It doesn't matter if this is strictly less than or equal, that's fine. So how do you find this? Always C mean standard normal distribution. Okay, we are dealing with standard normal distribution. So you can locate to 2.85, I think from the second table, yes, from the second table, and find the particular area. Okay, so that I can tell you that value definitely what? Greater than 0.5. Okay, probability for let's say area for not area, let's say probability. Okay, probability for all positive values, all positive C score values or C values, definitely greater than probability what? Greater than 0.5. Okay, so in the next one you can see that once you find the value, it's going to be 0.9978. Okay, once you need to find the C value greater than 2.85, you can use the negation 1 minus the previous one, part A. Okay, this means something up to this point, 2.85, this one. This one asks this area, right? So 1 minus that first area, you can find the second area under the curve. Clear? So remember that normally I call area, sometimes I call probability. They are similar. Okay, this case they are similar, probability or area, they are similar. Okay, so don't confuse if I use area, sometimes I use probability. Okay, if you need to find the probability in between two values, first, okay, I'll show you how to split this into two pieces, right? First piece, you can, let's say this one, you can write Z greater than negative 1.66, right? Yeah. Next one, this one, probability Z less than 2.85. Clear? So this is how we break this given case into two pieces. Okay, which means simply in between these two, right? Negative 1.66 and 2.85. Right? So it doesn't matter whether it is equal or not, same. So what you need to find? First, you need to find these are the two values, negative 1.66, this is 2.85. So first you need to find the area from it is let's say negative infinity to this point. Okay, this area, and then you have to subtract this area. Clear? So that you can get what you need, this area. That's what they have done here. This belongs to C less than 2.85, the same value here. And this is the Z greater than this one, negative 1.66. Oh, sorry. Okay, clear? Oh, hold on. No. This is 1 minus. Okay. Is this correct? I mean, this is correct, right? This one, that's correct. What about this one? Oh, this is correct. Yes. You need to find the probability up to this point. So probability up to this point, less than case, up to this point, value is this. I just confused for a moment. Okay, clear? So this is this. So you need to subtract and get this area. Clear? It's right. Okay. Any questions? Okay. I think that's okay. I think I can finish from here. Okay. This is what I was talking about in the first place. If we don't have a normal distributed case, like if we don't have a standard normalized, not normalized, standard normal distribution. Okay. If we don't have a normal standard normal distribution, still we can convert our normal distribution to a standard normal distribution. Okay. So remember that we can convert our normal distribution to a standard normal distribution. Okay. This is how we do it. This process we call standardization, or sometimes we call normalization. Standardization or standardizing. Okay. So this standardizing, how we do this? This is your why we use C, because it is the notation for standard normal variable. Okay. C equals your x value. X value come from this, your normal distribution. X minus it is expected value or mean divided by standard deviation. Okay. This is the mechanism to convert your normal distributed variable to a standard normal distribution, and standard normal distributed variable. Okay. Or simply normal distribution convert to a standard normal distribution. This is the mechanism, or this is the process.